I'm going to wish you happy afternoon, everybody. And let's get started. Welcome to another exciting afternoon of Organic Chemistry, Chem 170, with your host, me, Dr. White. And hopefully you're ready for a really good day. Excuse me, I am. All right, couple things. First of all, I thought about it this morning, I forgot to, and sometime today or tomorrow, I'll put out an email postponing test number 1 by 1 week. Instead of this Wednesday, it'll be the next Wednesday. Oh, how do you like that? Anyways, it'll be next Wednesday. This gives me time to go through the practice problem sets with you for the test we've already done. Today we'll do ethers epoxides, and next Monday we'll do the ketones and aldehydes because I'll finish that chapter probably either today or Wednesday. All right, a couple of you are a little behind your labs. I'm going to do an amnesty program. You have until Sunday to hand in any labs you haven't done yet, and I won't take any points off. This is the only time I'll do amnesty this semester. So hand in your labs, please. You don't want to lose points on labs. They're not that hard. If there's the assignment area in D2L is no longer available, email me with your labs when you're finished it. If you don't have the labs, email me and I'll send you a copy of the lab to do. Remember, if you have any problems with anything, including labs, always feel free to come to my office hours, which are Monday and Wednesday night from 6 to 7:15 on Zoom, which is located in the syllabus link for that and on the front page of the Chem 170 D2L front and introductory page. Now, one of the things I have going to be doing more this week, and also I've come up with an exciting idea that may help some of you out. During my office hours, Monday and Wednesday night in Zoom, I can set up breakout rooms. And if any of you want to meet with any of your colleagues to talk about whatever, feel free to come to my office hour and I'll set up a breakout room for you. That way you guys can work with each other. Also, this Wednesday, I didn't do it last Wednesday because I was quite busy trying to finish up some stuff. We'll do breakout rooms for the lab. And I'll get to meet some of you more on a one-on-one or one-on-5 basis. And I think that's a good thing too. All right, with that, let me look at my notes. I got everything covered I wanted to. Anybody have any questions before I start? All right. Everybody should see the ether epoxides problem set. Thank you. And let's go through it. Let me just make this a touch larger. All right, let's look at the following. And if you notice, I don't have any nomenclature for ethers or epoxides, hint. But anyways, give the organic product or products for the following. And always look at a molecule, look for what's different. What's not a carbon-carbon single bond or carbon or oxygen, carbon hydrogen, I'm getting ahead of myself here, should get your attention immediately because that's where something will happen. That's where all the action is. That's where the fun is. Now, if we look at problem 1A, we'll see that, oxygen with a minus charge, sodium cation, alkoxide, even though I won't ask you what it is. This should be R prime. I noticed a mistake. Oops. But anyways, carbon, halogen, alkyl halide. Remember, X can be chlorine, bromine, or iodine. And what do you get? You get an ether plus a salt. Now, since I'm asking for the organic products, you don't have to write the salt down, but if that helps you, feel free to. And now this is our R, this is our R prime. Listen carefully. Oxygen here bonds to the carbon in the alkyl halide that has the halogen on it. So methyl R, 3 carbons. Remember, you don't break carbon-carbon single bonds. And to the end carbon, and you get methyl and propyl ether. If we look here, same thing. What's different? Oxygen minus charge on a carbon, sodium cation, alkoxide, carbon-carbon. Ooh, halogen, alkyl halide. This attacks that. You know, organic chemists are violent, but in actual discussions, that's how we say that. The oxygen attacks the carbon with the halogen and bonds to it, kicks out the bromide, and you get sodium bromide, which you don't have to put down unless you want to. All right. Any questions? I should do this. Any questions on the first page? Going once? Going twice? Let's move on. Oh, before we do that, I'm going to do something. Oh, I got to turn my writing pad on. I had it off. Wonder, oh, why isn't it working? No, it's working. And here's one for your fun and enjoyment on this beautiful afternoon. What are the organic products or products for the following 3 points each? And I'm going to let you have a little fun too. And while you're working on the product, or this problem, and getting the product or products for this organic, I would like to thank you for being in my class and remind you, remember, in my class, in my world, in my universe, there's no such thing as a dumb question. Always, always feel free to ask questions in my class or outside of my class, anywhere around me. I'm going to try to poll again. All right, looks like just about everybody's done. So I'm going to move forward and let's do this. Question is, what's the organic product or product for the following? How do you do that? You look at the reactants, starting materials. What's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon? Ooh, cations. We have R group carbons, alkoxide, oxygen negative, sodium plus. Carbon, ooh, halogen on a carbon, alkyl halide. Remember, X here can be chlorine, bromine, or iodine. And what do you get? You make an ether. You also get sodium salt, but this is inorganic. Remember, the oxygen bonds to the carbon in R prime that the halogen is attached to, and that's where this is. So what's R? 2 carbons. What's R prime? 4 carbons. And which carbon has the halogen? That carbon. So I'll draw my 4 carbons. Then I'll have my oxygen. And then my R group is 2 carbons. And I know there's 4 bonds to carbon, so I can put in my hydrogens. And I forgot 1 carbon, now it's there. And that's how you do it. You made an ether. Now, next question, parts, D and E. If we look at this, let's look at D first. What's different? Carbon, 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 carbon. Ooh, oxygen. What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Should get your attention, got mine. And what do we have here? An alcohol. And here, what, ooh, 3 atoms, well, actually more than 3. 2 carbons and oxygen in a ring with hydrogens, that's ethylene oxide. Alcohol, 1 mole or molecule ethylene oxide gives me this ether alcohol. In this case, what's R? 4 carbons, you break carbon-carbon single bond? No. Now the carbon with the hydroxyl group is the carbon this oxygen is bonded to an R, and therefore R is 4 carbons, oxygen, CH2, CH2. Now, in E, Dr. White did the standard trick on an organic chemistry test by the instructor, put a big, scary molecule. But if you know what to look for, it's not scary or big. Well, it's not that big, but anyways, what's different? A ring, nah, this is carbon-hydrogen bonds, carbon-hydrogen. Ooh, oxygen with a hydrogen, hydroxyl group on carbon, alcohol, ethylene oxide. This is my R group, and this is the product you get. And I made one even more scary, not really. Well, again, here's the hydroxyl group, 1 mole, follows this general reaction, and you get this ether. And the R group, the carbon with the hydroxyl group is the carbon this oxygen, and OCH2, CH2OH is bonded to. And why don't you have one to try on your own? And that would be, what would be the organic product or products for the following reaction, 3.Cs? Someday, I'm gonna, well, I know what day. Wednesday, if you can, please make sure your webcam is working, because during the breakout rooms, I'll ask you to turn them on. That way I can see your real people behind the names on the screen. Let's try this time. When you're done, give me a thumbs up. I already see one person done. I think everybody's done. So let's do it. And the question is, what's the organic product or products? Remember, these reactions are how chemists, like myself, organic chemists, build new molecules, excuse me, to use in various things. And we look at this molecule, what's different, what's not carbon, what's not hydrogen. Ooh, an oxygen with a hydrogen on carbon, alcohol. Ooh, oxygen, a ring with two carbons, ethylene oxide. And what do you get? You get this ether alcohol. And what's my R group? This. Which carbon has the hydroxyl? That one. Well, this tells me it's still going to be there. You don't break carbon-carbon single bonds. I'll still have this methyl group and this methyl group. Then I'll have my oxygen, CH2, CH2, OH. And there you go. And let's move on. Now, if we look at G, well, we got a benzene ring, but benzene will not react with ethylene oxide. Ooh, carbon with a hydroxyl group, phenol, an alcohol. And then here we have, ooh, that's different, a coefficient, a number in front of the ethylene oxide, 9. And this is ethylene oxide. And now the general reaction is an alcohol plus N moles of ethylene oxide gives you this poly, remember that means many, ether alcohol, where I'm using the parentheses to denote a repeating unit, how many times N, which comes from here, and outside the alcohol will be OH. Common mistakes students make. They put the alcohol inside the brackets. That's wrong because nothing like that exists. So what's R? Benzene ring. What's N? 9. I'll have my benzene ring attached to the parentheses oxygen, CH2CH2, close parentheses, N is 9, OH. And this one here, R is 4 carbons, N is 5, same reaction right here.
Dr. White?
Hey.
Hi. I'm having a little difficulty with my eyes and my hands going in the direction I want. I was wondering if you can scroll back up to the 3 point, the first one you did, yeah. CH3.
CH3, CH2O minus Me plus, CH3, CH, CH2, CH3, Br. And then right here, you have CH3, CH, CH2, CH3. On the second carbon, you have an oxygen. You have CH2, CH3. Got it?
Yeah.
All right. Now, one thing, I will go back like that, and it's always a good question. But since I'm caught up with my videos, you can always go to YouTube too. If you ever have a question, what did he write back there? But
Thank you.
You can still ask it in class because there's no such thing as a dumb question. And I was about to do a problem, so I don't want to cheat you out of some fun. And the question would be, what's the organic product or products for the following reaction? While you're doing that, I'm going to cheat a little, not really cheat. All right, I know where I ended up now last week, because I can go back and look at the video. For those who are wondering, I use a GOM, I guess it's pronounced GOM viewer. That's the best one out for looking at videos in my personal experience. The stuff that Microsoft gives you, I don't like their viewer. All right. Oh, by the way, if you're interested, where do you get a GOM viewer? How many of you have heard of the site File Hippo? File Hippo, go to Google, put it in there. It's the best place to download free downloads and different software. GOM viewers on there. All right, I think everybody's done. Let's do this. And the question is, what's the organic product of the following products of the following reaction? If we look at this molecule and say, what's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Ooh, oxygen with a hydrogen and a carbon. That's an alcohol. What? Ooh, 11 ethylene oxide. I'll call that N. And what do you get?
Hey, Dr. White.
That's great, Martin.
I can't see the screen.
Oh no, I forgot to ask the thumbs up people. Can you see it now, Martin?
No, I still have a blank screen.
Oh no. Does everybody else have a blank screen too?
No.
Are you having?
I'm gonna try exiting out and then coming back. Let's see.
All right, I think it's your, hold on before you do it. The other people, give me a thumbs up if you can see my whiteboard when I do. Thank you. I think you're having a technical problem, so why don't you log off and try logging back on again, okay?
Okay.
Maybe he's got a bug in his system. By the way, does everybody know where you got a bug in the software comes from or system? Back when they had the original computers, which were tubes and a lot of wires, they first started doing stuff with computers. They had a major problem. What happened was a cockroach got into one of them, bit on a wire, shorted it out, and messed up the computer. And that's where they have, you got a bug in there. I think it was after that. Turing, Isn't that the one with wheels and mechanical back in the 1700s? I'm talking about the 1940s, 1950s era. Well, could have been that one too. I'm not sure. I'll have to look it up, or I'll let you look it up. All right, let's do this problem. Now, let me see the Martin. Martin, are you back with us where you can see the screen?
Yes, I can. Sorry about that.
Nothing to be sorry about. We're dealing with technology that we're pushing to the envelope, the limit, teaching and all that, and stuff happens. All right, let's get to work. What do I have here? Alcohol. What's my R group? This. What do I have here? N moles of ethylene oxide. I get my polyether alcohol. Do you break carbon-carbon single bonds? No. So my R group, 3 across, methyls here. Which carbon has the hydroxyl group, this end one? That will be attached to the O, CH2, CH2, close bracket, OH. What's N? Ooh, I forgot to finish this. N is 11, and I know there are 4 bonds to carbon. And that's how you get your right. And oops, oh no, I forgot a hydrogen. Don't look. All right, you can look now. And that's how you do it. Now, one of the interesting things, molecules like this and other R groups are used heavily as, I'll teach you later, a group of compounds or type of molecules called surfactants. And Dr. White worked in the surfactant industry for many years. So that's how you do it. Ooh, you probably haven't thought of this, but if you use any personal care products like hand lotions, shampoo, soap, and other things, organic chemistry, and especially in personal care, including cosmetics, these type of molecules are heavily used. But you never thought cosmetics and personal care are very sophisticated organic chemistry. They are. Now, with ethylene oxide reaction, either both of those, I will never ask a synthesis problem, but with ethers, I will. And here we have one. Give the starting materials for a following reaction. Well, you look at the product and what's different? Oxygen, carbons here and here. And I gave you, which is unusual, an inorganic product, sodium halide. And it's the ether. Sodium is salt. And how do you make an ether? Williamson ether synthesis, R prime, RO minus, Na plus, alkoxide and alkyl halide. Now, I can say the methyl is R and the ethyl is R prime. And if that's the case, then R is methyl, R prime is ethyl, and the halogen is bromine. And I would get this, but wait, I can call the methyl R prime and the ethyl R. In that case, the ethyl is R with an alkoxide, O minus, Na plus, and R prime is methyl, the halogen is still bromine. And both reactions will give you this product. However, one is cheaper than the other. How do you know? You don't. I'll never ask on a test. Both these are acceptable, but in real life, the bottom one is cheaper than the topper one, cheaper meaning lower raw material costs, which means you get a greater profit. Now you know Dr. White's worked in the chemical industry.
Dr. White,
Yes.
on that problem, the oxygen is a electrophile. CH.
Oh, actually, it's a nucleophile.
Nucleophile, okay. And that's going to attack the carbon
of the
next to the bromine?
one of the problems with this class is I only have one semester to teach you organic, the important parts. So I can't do mechanism, but nobody tells, I'll do a taste of one just to show you. Here's stuff I haven't taught you because I won't be on a test. But, all right. This oxygen is looking for positive, looking for anything that's supposed to be a Y, positive. Now, this alkyl halide, what you don't know, but I'll teach you right now, is when you have a carbon with a halogen, where X is chlorine, bromine, or iodine, like a ketone, which I taught you. This I didn't go through. This is slightly positive. This is slightly negative. There's a difference in electronegativities. Therefore, this carbon has a slight positive charge, and is why this attacks that. And it's called nucleophilic attack or nucleophilic reaction, addition to this, because this carbon is slightly positive. When it gets attacked, the electrons here go there. And Dr. White just had a lot of fun. It also won't be on a test, but now you know everything you wanted to know about that.
Thank you.
And everybody who I just lost, take a deep breath, relax. I'll never put that on a test, but I should tell you, and it's partially because of I've got a PhD in organic chemistry, and more partially because my research advisor, when I was at Michigan State, beat into all our heads, understand the mechanism for every reaction. That way you can do serious good. He didn't put it that way. Over the years, I've changed it, but he always demanded that anything we were doing, any reaction, you better know the mechanism, or how can you understand it? How can you make it do what you want it to do? Now, in this class, I'm not showing mechanisms because I just don't have the time. I need 2 semesters, and that's the different course which Dr. Daly teaches here.
Thank you.
You're welcome. And thank you for letting me have some fun. Now you know I'm an organic chemist. All right.
You're welcome.
And now, oh, let's do B. All right. Now, one thing I just realized, I should never put C on there, put an X through it. Nah, it's not there because I'll never ask that kind of question, synthesis with ethylene oxide on the test or the final. But B, I can. And the question is, what's the organic product or products for the, what's the starting materials for the following? And by the way, Dr. White is going to be real nice. If there are 2 starting materials, notice I gave you 2 question marks, let you know that. When I took this stuff, our instructor didn't do that. So shh, don't tell anybody, I'm being nice. So if we look over here, what's different? Oxygen, carbons here, carbons here. And what do we have? An ether. Oh, we also have a salt, sodium iodide. How do you make an ether? Williamson ether synthesis, an alkoxide alkyl halide. So I can say this N-propyl group is R. Notice the N carbon has the oxygen, and that will be this alkoxide. Now, here we have 3 carbons, and the center carbon, an isopropyl group, is bonded to the oxygen, and that will have the halogen, which is iodine. But wait, I can call the isopropyl R, and that's got the oxygen with the minus side and the sodium cation, the alkoxide. And then this group, the N-propyl, the N carbon is to oxygen, so the N carbon will have the iodide. And both will be correct answers on the test or the final. And why don't you try this one for your fun and enjoyment on this beautiful afternoon? You can tell spring is coming because before the class, I happened to look out my front window and across the street, I saw our mailman and he had shorts on. So spring is in the air, but be careful. It can still snow here. See, one person's done. And don't rush, I'll give you another minute or so. See some more. Oh, you know what Dr. White's going to try? All right, it looks like everybody's done. So I better get to work. All right, question is, what's the organic product or products for starting material? I keep on doing that. What's the organic starting material or materials for this reaction? Remember what you start with to call the reactants, but if you work in the chemical industry, I will call the starting materials. So I look at the products and say, what's different? Well, this one, oxygen, got my attention, and I have an ether. And here I have sodium halide, a salt. X can be chlorine, bromine, or iodine. In this case, it's chlorine. And how do you make an ether? Williamson ether synthesis. So if I look over here, I'm going to call this R, and my ring here, R prime. In that case, R is methyl, so I'll get this compound. By the way, yes, there's IUPAC nomenclature, which I'm not asking you to learn. That'd be called sodium ethoxide. And then here I have my ring, and here's my carbon. And what's the halogen? It would be chlorine. But wait, I can call this R prime and this R. If that's the case, R is cyclopentane ring. And I have my oxygen, sodium, cation. What's R prime? R prime in blue is methyl. And my halogen is chlorine. So the question is, here's A, here's B, which is right? For my class, both. In real life, I would think B would be cheaper, but I'd have to look up the prices. And that's how you do that. Any questions on the ethers, epoxides problem set? In a classroom, I definitely wouldn't be doing this. All right. In light of the beautiful weather outside, let's play that exciting new game, circle and name the functional groups. And how do you play that exciting new game? And if we were face to face, you'd be watching me write this on the whiteboard. Let's call this one F. Let me do E over here. Ah, E is right here. And here, all you have to do is circle and name the functional group, 2 points each. Don't name the molecule. And have fun. While you're doing that, I'm going to look out into my weather window, otherwise known as weather underground, and see what the temperature is outside. And where I live, it's a balmy 59 with nice wind. So after class today, I'm going to do it again, open my windows in my house and give it a nice, almost spring air out. Sorry about that. I hope you're all enjoying playing that fun game, circle and name the functional groups, 2 points each. Oh, it warms my heart to see everybody working on their organic chemistry on this beautiful afternoon. Thank you. All right, looks like just about everybody's done. So let's go ahead and do this. All right, how do you play this game? You look for what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention. Oh, look, carbon with a hydroxyl group on it. You don't have to write this down, but I will. It's an alcohol. I can spell it right. Oh, it's awful spelling Monday. It's an alcohol. Next one, B. What's different? Carbon, carbon, carbon. Ooh, carbon, double bond to oxygen with a hydrogen and a carbon. It's an aldehyde. Next one, carbon, carbon, carbon. Remember, look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. Ooh, oxygen, double bond to carbon. Notice our carbons here, and we have a ketone. Remember, ketone is not spelled with a Y. Students like to put that in there, but I don't take off spelling on my test. All right, let's look at the, ooh, this is getting interesting. There's an oxygen there, that's different. There's an oxygen there. This one on a carbon, alcohol. Carbons here to this carbon, double bond oxygen. What's that? A ketone. And let's look at E next. And what do we have? Carbon, carbon, carbon. Ooh, oxygen right here. With carbons here, carbons there. What's that? Ether. And finally, the last one, which I'm going to redraw down here to give myself some room. And if we look right here, I've got an oxygen double bond to carbon with carbons and a hydrogen. And what is that? That's an aldehyde. Ooh, carbon double bond to oxygen here with carbons here and here. What do we have? A ketone. And finally, right here, carbon oxygen, carbon, and what's that? It's an ether. And that's how you play that fun game, circle and name the functional group. Got a minute or two past our break time. I'll still give you your full break, but listen carefully. If you don't know how to play circle and name the functional group, 2 points each, well, you look at a molecule, how are you going to name it? You need to know the functional group. If you're going to react the molecule, how do you know what you're dealing with? You have to know the functional groups. What's different? And finally, if you're trying to determine how do I make something, well, what functional group are you trying to make? And therefore, it's critical in organic chemistry to always be able to know how to play that fun group game, circle and name the functional group, 2 points each. And that's how you do it. And that's something you should practice. And whenever you're doing a reaction, you should know what functional group am I dealing with by looking at what's different, what's not carbon or hydrogen, what's not a carbon-carbon single bond, and that will teach you where to look at it. And also you should be able to name it so you understand what reactions are going on. And with that, let's be back at 5 minutes at 2 o'clock. That's when the big hand, if you have an analog watch, is on to 12. And I'll see you in 5. I'm going to go stretch. right, let's get back to work, everybody. Ring, ring. Oh, wait a second. Never let the little kid in you disappear. I haven't. I used to be enjoyed. All right, speaking about enjoyment, I hope you all followed the news, and hopefully this week the House will and the Senate will finalize the special COVID relief package. I forgot the official name. That's a huge, huge good thing for Americans. And I guess we all have Stacey Abrams to thank for that because of what happened in Georgia, thank goodness. But anyways, enough politics from Dr. White. Let's get back to some organic chemistry. Now, last week, I was going through 4 reactions of aldehydes and ketones. Let's go through that again briefly today, and then we'll move on. All right, first reaction we talked about is the reaction of an aldehyde or ketone. Remember, when R prime is H, it's an aldehyde. When R prime has carbons in it, it's a ketone. And reacting it with an alcohol, and H plus is acid catalyst like sulfuric acid. Keep your eye on the carbonyl carbon. That's where the fun is. And this gives you this hemiacetal or hemiketal. What's attached to what was the carbonyl carbon is still attached. You have a hydroxyl group, oxygen, another oxygen with R from the alcohol. And if we look at this reaction, what do we have here? What's different? Double bond to carbon, carbonyl group with the carbon's hydrogen. This is an aldehyde, but it could have been a ketone. Carbon-carbon hydroxyl group. See, it's important to be able to name that functional group. Alcohol. And then acid catalyst. Keep your eye on the carbonyl carbon. That's where all the fun is. What's attached to it stays attached to it. Hydroxyl group, oxygen, then R, no R prime there. And there we go. And if we come back here, I'll call this R prime, this R double prime, this R, remember that should be 2. The carbon with the hydroxyl group is the carbon this oxygen right here is bonded to. So keep your eye on the carbonyl carbon. What's attached to it, R prime, hydrogen, R double prime, methyl, hydroxyl group. Oxygen was R, ethyl. And that's how you do it. Now it's your turn. And there you go. And remember, by sometime tomorrow, hopefully, unless somebody gives me $1 billion, don't hold your breath on that, I will have a video of today's lecture posted in the Chem 170 YouTube channel, which is internationally renowned. I wish. And for those who are quicker than the others, please be patient. If we were in a classroom, I'd be saying the same thing. The only difference in a classroom, I'd say, when you're done, look up and smile. All right, anybody need more time? All right, let's do this. If we look over here at the reaction, what's different? Well, this first thing, ooh, carbon double bond to oxygen, carbons here and here, that's a ketone. In this case, it's a cycloketone, a ketone in a ring, where our prime and our double prime are connected together. Carbon, carbon, carbon hydroxyl group. And here we have an alcohol, acid catalyst. Keep your eye on the carbonyl carbon. What's attached to it stays attached to it. I'm talking about carbons or hydrogens. This becomes an alcohol. It's not really an alcohol, hemiacetal. And then you have our group. I call that our prime and our double prime. Therefore, and then this carbon is this carbon right here. And what's attached to it? Hydroxyl group. Then oxygen was R and propyl. And that's what you do. Now, if you have two molecules or 2 moles, remember mole is the counting unit of chemists, and react it with an aldehyde or ketone, when R prime is hydrogen, aldehyde, when R prime is carbons and hydrogens, ketone, what you get now is the acetal or ketal, which I'll never ask you the name of these on a test, but I'll use them. And since I've already done this, I'm going to see if you're up to the challenge. Now I'm going to let you try this on your own, and then I'll do it. What would be the organic product or products for the following reaction? And I'll teach you later on, Mother Nature uses this type of reaction to make all the wonderful starches in our life. You know, the good stuff that makes up things that Dr. White shouldn't have, like pizza, potato chips, French fries. Challah with butter on it. For those who don't know what challah is, it's egg twist bread that you get at a nice Jewish bakery. Or other ones that make it, but it's usually Jewish ones. Oh, now I'm getting myself hungry. No, not really. I had lunch recently. All right, it looks like everybody's done. If not, feel free to come back to the video or see me after class today. I'll help out. Now, first thing, what are we dealing with? What's different? Ooh, oxygen, double bond to carbon, carbonyl with carbons here, and what do we have? We have a ketone. Now, if R prime was hydrogen, it would be an aldehyde. And ooh, we're reacting with not one, but two molecules of an alcohol. Acid catalyst. Keep your eye on the carbonyl carbon. That's where the fun is. By the way, I think I mentioned, Dr. White, if I were to be honest and somebody asked me, what kind of chemist are you? The only answer I could give is a carbonyl synthetic organic chemist. Dr. White loves carbonyl groups. And what's attached to it is still attached to it. And then now we get two oxygens. Each one has the R group from the alcohol. If I come here, I can call this R prime or R double prime, doesn't matter which. And I have here my alcohol R group. Oops, no R prime there. Dr. White, I think, is suffering from R prime overload. And one thing I should mention, the carbon with the hydroxyl group in R is the carbon this oxygen is bonded to in our acetal or ketal. And now I keep my eye on the carbonyl carbon because that's where the fun is. What's attached to it, R prime methyl, R double prime ethyl. Then on that carbon, I have two oxygens, and then my R group is isopropyl. Notice the center carbon has the hydroxyl group. That carbon is carbon bonded to this oxygen here. And this should be, let me clean it up. In real life, sometimes when I run out of room on a board and I don't think ECC wants me writing on the walls, I rewrite it to like that. And there you go, and that's how you do it. Now, once you have these compounds, what can you do with them? Well, Mother Nature provided us a way, and that's if you have a hemiacetal or hemiketal, and react it with acid and water, or you could have put down water and acid, you get back the aldehyde or ketone plus the alcohol you would have used to make this. So if I do the following, and I'll ask you to give the organic product or products for the following. And the reason we're going over this again is because historically, I've seen students have a lot of problems with these, and practice makes perfect. Or in your case, helps you do better on test number 2, which I also get what I want. You've learned this material. See how sneaky Dr. White is? And by the way, everybody, thank you for coming to my class today. All right, it looks like everybody is done. Let's move forward. How do you do the problem? Look for what's different. And this is one of the two cases in all of organic chemistry where you have two oxygens bonded, singly bonded to the same carbon. And that's either hemiacetal, hemiketal, or next reaction I'll show you too. And notice here, I have a hydrox group oxygen with carbons. I'm going to call this R. This hydrogen I can call R prime, and this methyl R double prime. If you look up above here, keep your eye on this carbon, which becomes this carbonyl, carbon double bond to oxygen. What's attached to it is R prime, hydrogen, R double prime, methyl. And then my alcohol, the carbon with the hydrox group here, or with the oxygen, becomes this carbon with the hydroxyl group. And we have 3 carbons, because you know you don't break carbon-carbon single bonds. And that's the product you get. Let's do one more of these review. And the reaction, I'll help you out. If you have right here an acetal or ketal, R prime can be hydrogen, acetal, carbons, ketal, acid, water, and keep your eye on the carbon. Here again, there's only 2 places where you have oxygen, 2 of them single bonded to a carbon. And what you get back is the carbon with 2 oxygens comes the carbonyl of a ketone or aldehyde you would have used to make this acetal or ketal. And then you don't have to put the 2 there. That's why I'm making it as small as possible with the quotes. You get an alcohol, and that comes from here. And have fun. Your turn. All right. I think everybody's just about done. Let's do it. All right. What's different? Ooh, not one, but two oxygens to the same carbon right here on the ring. And each oxygen has carbons. So what do I have? I have this. Now, this carbon with the two oxygens has carbons here and carbons here. And I'll call those R prime. Could have been hydrogen, but it's not. And R double prime. And just so happens R prime and R double prime are connected in the ring. And when you add acid and water, otherwise known as acid hydrolysis, which you can get from your stomach, which I'll teach you this reaction, you get back the aldehyde or the ketone you would have used to make this acetal or ketal plus the alcohol. I'm only asking for the products, but if you want to put two there, you can. So this is my R group. I'll call this R prime, this R double prime, and they're connected together. So I'll start with this ring. Still has the methyl group. You don't break carbon-carbon single bonds. The carbon with the two oxygens will be the carbon double bond to oxygen, the carbonyl. Then my R group is methyl, and you'll get methanol. And that's how you do that. As I said, these four reactions I will never, ever put on a test as a synthesis problem. That's not fair. And Dr. White tries to be fair. Whoa, where'd you go? All right. Next couple slides. Dr. White's going to have a lot of fun because I'm going to talk about my hero in organic chemistry, Victor Grignard. Let's look at why he's such an important figure in organic chemistry. First thing I have to teach you is the Grignard reaction. Again, Victor Grignard is one of the greatest of all organic chemists, a French organic chemist, and he won the Nobel Prize for the next two reactions he discovered. I like invented, it sounds better. And the first thing is the formation of the Grignard reagent, named after him. And here you take an alkyl halide plus magnesium, and you get the Grignard reagent. Now, it's important to remember that R is bonded to the magnesium is bonded to the halogen. Here, X can be chlorine, bromine, or iodine. It's not the other way around. So let's take a look at this. It's a fun reaction. It's fast, it's easy, and it works well. Fun reaction. If we look at this reaction, first thing is identify what's different. Halogen on a carbon, alkyl halide. Remember, X can be bromine, chlorine, or iodine. Ooh, magnesium, metal, that's different. And you form the Grignard. And remember, it's the carbon with the halogen is bonded to the magnesium, which is bonded to the halogen. So what's my R? 4 carbons. Then I'll have magnesium. What's my halogen? Bromine. And I know there are 4 bonds to carbon, so I can put in my hydrogens. And that's the Grignard. This is a really fun reaction to run. And here's one for you to have fun with. Give the organic product or products for the following. And we won't cover it in this class, but yes, IUPAC has rules for how to name Grignard reagents. And when you're done, give me a thumbs up. I think everybody's done, so let's do it. If we look at this reaction, what's different, what's not carbon, what's not hydrogen, what's not a carbon single. Ooh, carbon with a halogen, alkyl halide. And I've got magnesium. You actually do use magnesium metal or ribbon, a very thin metal, or powdered magnesium will work too. And you form the Grignard reagent. And here, what's our isopropyl? What carbon has the halogen, the center one? So I have my 3 carbons. Now I have magnesium and then chlorine. And I know there are 4 bonds to carbon. What is wrong, and I'll mark it wrong, that's wrong. There's no molecule I know of in all of nature or anywhere else as a carbon bond to the bromine bond to the magnesium. This is wrong. Don't do that. I'm telling you that because students do that. Well, I would have had a chlorine here, but anyways, you get the feel. Oh, let's do one more of these because they're fun. Well, let's do a synthesis. What would you react with magnesium to make this compound? Have fun. All right, I think everybody's done. Let's do this. And how do you do this? You look at the molecule and say, what's different? Ooh, I've got a carbon with a magnesium, and that magnesium is bound to halogen. I have a Grignard reagent. And what do you react magnesium with? An alkyl halide. What's my R group here? This. And therefore, I'll have my ring, my methyl group. What carbon has the magnesium iodide? In this case, this carbon, which means the halogen X, and X here, which X can be chlorine, bromine, or iodine. is an iodine, and that's how you do it. And that's the Grignard reagent. And it's real easy to make. Usually you do this in ether. And in a 2-semester course I've taught, when I was at Michigan State, I taught the lab for that. When you made a Grignard, you'd put it in a round bottom flask and use it in ether. Now, ether is very flammable, as you learn. So how do we have them heated up so they didn't burn their lab down? With your hands. Your hands, your body temperature is enough temperature to make a Grignard reagent synthesis go. All right, now, once you have the Grignard reagent, what can you do with it? Well, you do what Victor Grignard find out. Oh, I have to. Oh, let me check. Everybody see the nice picture of Victor Grignard there? Don't you love that mustache? That's a pretty mustache. All right. Now, Victor Grignard won, I think it's the 2000 or 2000, I'm off by a century, the 1905-1910 Nobel Prize for the Grignard reaction. And I'm trying to look real quick, which means I'm not going to find it. No, it doesn't say when he wins it. But anyways, great organic chemist and my hero. Now, once you have the Grignard reagent, what can you do with it? You can react it with ketones and aldehydes. Now, before I go over the Grignard reaction, I need to talk about something we haven't encountered before then. What happens if you have more than one reaction? You're going to run the other. Organic chemists are lazy. And let's say you have A, and you're going to first react it with B. Let's do it the old way. And then whatever you make here, you'll further react with C to make D. Well, how do organic chemists do this when we're lazy? We go, first step, you react A with B. Whatever you get, you react it with C, and then I'd make D. So first you react A with the first reaction above the arrow, and then you react whatever the mixture is or whatever the product in A and B, you then react it with C. Well, with a Grignard, you do the same thing. Well, you do the same type of style. Everybody got this down? I think so. So let's look at a Grignard. You start with a ketone or aldehyde, and then now sometimes if our triple prime, yes, I can go up to 3. Grignard is too long. I'll put it here and then second step 2. And second step, acid and water. Now, because the carbonyl is polarized, the Grignard reagent, which is like, but not really, R plus MgX minus, it's like this. It reacts like it is, but it's not truly that way. This carbon with a slight or full positive charge doesn't like it. It's looking anywhere. Oops, I did it backwards. Must be the sun outside. Carbon with a minus charge is very reactive. I've worked with some of them. I've worked with Grignard reagents, and it's saying, where's anything positive so I can bond to it? And this carbon with the Grignard attacks this, opens it up. Second step puts a proton on there, and you get a new molecule. That's an alcohol. Now, what's special about this? The new bond, you've made a carbon-carbon single bond, and that's very rare, very special, very useful in organic chemistry, and that's the Grignard reaction. Now, on a test or a final, I'll never give a synthesis for the Grignard reaction, but I will for making the Grignard reagent. So let's take this out for a fun drive. By the way, tonight at midnight, I'll be giving speed drawing classes. No, I won't. But don't forget, public service commercial from Dr. White, announcement and commercial. Don't forget office hours tonight at 6 to 7:15 on Zoom. You've got the link in both my syllabus and on the Chem 170 homepage. And if you have any questions, always feel free to stop by and say hello. So if we look at this reaction, question is, what's the organic product or products? What's different? Well, carbonyl with a hydrogen, but it could have been carbons too. And carbons here on that carbonyl. Remember, carbonyl, carbon, double bond to oxygen, a ketone or aldehyde. In this case, it's an aldehyde. Then first thing, carbon, magnesium halide, that's different, a Grignard. Where X can be chlorine, bromine, or iodide. Second step, acid and water. What's attached here originally to that carbonyl is still attached. This opens up to an alcohol, and now we do that special thing, make a carbon-carbon triple, carbon-carbon single bond. What's my R prime? Hydrogen. What's my R double prime? Ethyl. What's my R triple prime? Methyl. Keep your eye on the carbonyl. That becomes this carbon right here. What's attached to it? R prime hydrogen, R double prime ethyl. And it has an alcohol. And now that new carbon-carbon single bond was our triple prime methyl. I know there are 4 bonds to carbon. In a very simple way, I've made a carbon-carbon single bond. Now, one of the questions you should be asking yourself always is, why am I learning this stuff? Well, I won't go through it now, but by the end of the semester, I'll show you how putting a certain group, modifying a carbonyl, has changed our world. And what I'm talking about is birth control pills. And by using a similar type of reaction, organic chemists were able to take a cheap molecule, turn it into something a woman's body thinks is a steroid, which is how birth control pills. Remember, in this class, I'll talk about things that I'm not making a moralistic judgment. I'm just showing you organic chemistry and how it's affected our lives. And it's your turn. What would be the product or products you get, organic products, when you react this compound first with this and then with acid and water? Have fun. Now we're getting into the good stuff of organic chemistry, and Dr. White is happy. Remember, I'll never give a synthesis on a Grignard reaction. And as the votes come in, it looks like we have a winner. Time for Dr. White to get moving. All right, let's take a look at this reaction. Again, identify the functional groups. What's different? What's not carbon? What's not hydrogen? Ooh, carbonyl. Carbon's here. Carbon's here. Remember, carbonyl, carbon double bond oxygen. And this could have been an aldehyde, but it's a ketone. What do I have up here now? Ooh, carbon-carbon magnesium halide. It's a Grignard, where X can be chlorine, bromine, or in this case, iodine. Second step, acid and water. And what do you get? Keep your eye on the carbonyl carbon. What's attached to it is still attached to it, carbon hydrogens. Anything else too in this reaction. You get an alcohol and you make that special thing, a carbon-carbon single bond. And here's my R prime, R double prime, and R triple prime. Keep your eye on the carbonyl carbon, which is this one, comes in alcohol. R prime is methyl, R double prime, methyl, R triple prime, ethyl. And notice what we've done. We started with acetone, a simple ketone, a simple Grignard reagent. We've made a very, very, very complex alcohol in one simple step. And that's the beauty, and that's the power of the Grignard reagent. And I hear a question.
Yeah, it's me again.
Hey, you again? Go for it.
You know, I keep it's a stumbling block for me, but why uh in the reactants CH3R prime, why in the I guess in the formula is it hydrogen?
Well, that's because you could have done the reaction with an aldehyde too. This is the organic chemist's lazy way of, instead of writing two reactions, we combine them in one. What this tells me is if R prime instead of a methyl was a hydrogen, this would be an aldehyde.
Okay.
I have up here. And this also shows you when R prime is carbons, it's a ketone. So this is a way organic chemists, remember we're lazy, shows you how to write both an aldehyde and ketone, react with a Grignard, second step acid and water to give you an alcohol where you've done that special thing, formed a carbon-carbon single bond. Does that help?
Yeah, I mean, I get it when I'm doing the equations, but I guess I just don't understand why. But you explained it better. Thank you.
You're welcome. Well, the reason why is we're lazy.
Yeah. Okay.
Instead, here, instead of writing the reaction, general reaction like this, this is the word or, not organic chemistry.
All right.
See what I mean?
Yeah, I get it. All
And
right. Thanks.
it's a shorthand. I guess that would be,
Yeah. Okay.
that's fine. Oh no, I went over a little, which I won't cheat you out. Let's take a 5-minute break, come back at 2:55 and we'll continue. I can go look out the window and see if all the snow in my backyard is gone yet. I'll see you in 5. Time to start again. Let's go. Ring, 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 ring. All right, let's get back to the Grignard. Oh, let's have some more fun with this. I love Grignard reactions. Now, this is a case where it's too big to put something on top of the arrow. So I'll do one. The first step is this. These two are reacted, and second step, acid and water. Have fun. And I checked. There's still some snow in my backyard. Way the sun is in my backyard, my front yard, because of shadows. Usually I'm one of the last houses around to get rid of all the snow, even though most of it's gone. And the mountain by my driveway is just about gone too. All right, anybody need more time? Give me a thumbs up if you need more time. Or I played a game. I should say, give me a thumbs up if you're done. I was trying to change the rules like they're doing with the filibuster, which I hope they do. Anyways, this is chemistry, organic chemistry, not politics. All right, I think everybody's done. And if we look here, what's different? Carbonyl, carbon, double bond oxygen, carbon, 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 carbon. Ooh, magnesium halide, Grignard, second step acid and water. And if I write, I'll write it up here. Ketone or aldehyde, first step, Grignard, where X can be chlorine. X can be chlorine, bromine, or iodine. And second step, acid and water, where you could have also put down water and acid, same thing. And then what's attached to the carbonyl carbon is still attached. And then you have an alcohol, and then you make that special thing, a carbon-carbon single bond. Now, what's R and R prime? It's the ring. R double prime and R prime. And therefore, I'm going to still have my ring. You don't break carbon-carbon single bonds. I'll still have the methyl groups. Which carbon had the carbonyl on the ring? This one, which is this one right here. They'll have an alcohol. And what's my R triple prime? N-butyl. N-carbon has the magnesium halide. Therefore, that will be the carbon. And that's what you get. And let me just show you real quick why this is so versatile a reaction. I remember one time I was talking with some colleagues. And I don't know how this got brought up. But if you look at the following reaction, it's a Grignard. Here's my R triple prime. And this would be the product. And I know of no simple way to make this product without using the Grignard. With the Grignard, it's a piece of cake. Without it, I don't know how I could easily make that. And that's the beauty of the Grignard reaction. Remember, I'll never give a synthesis problem on there, on a test. Oh, hang in there. I don't know why this does this to me. It's the structures make all right. Let me just open one other file. And we're ready to go. All right. Now let's move on. And we can have, it's called reduction of a carbonyl group when you go from an aldehyde or ketone to a alcohol. It's called a reduction, but it's also called hydrogenation. And let me rewrite it in a way you're more familiar with. Bending the line is a carbon there. My software likes to do that. Hopefully you're all seeing this, and you're not. If you have reduction of a carbonyl, also known as hydrogenation, and I'm rewriting it, if you have a aldehyde or ketone reacted with hydrogen and a catalyst, catalyst just like you learned before, nickel, platinum, or palladium. Remember, carbonyl, you should know this, has just like a carbon-to-carbon single bond, has one pi bond and one sigma bond. And you know you can break a pi bond with hydrogenation, and each atom of the double bond gets a hydrogen. And this is a nice way of making alcohols. So let's take it out for a spin. First of all, let me give you a chance to write it down. I'll hydrate myself while you were doing that. That's a fancy way of saying I just had a drink of water. All right, everybody got this down yet? All right. If we look at this, what do we have? A ketone, but it could have been an aldehyde. Again, this is a case where instead of writing two separate general reactions, we combine it. We have a catalyst. Catalyst can be platinum, palladium, or nickel. And you break the pi bond. Remember, carbonyl, one pi bond, one sigma bond, and each atom of the double bond gets a hydrogen, which is attached to the carbonyl. Carbon is still attached to carbon. That is the alcohol. So if we look at here, our prime, our double prime, move me out of the picture here. What's attached to the carbonyl carbon is still attached, and you break the pi bond. Each atom of double bond gets a hydrogen. And your turn. What would be the product or products of the following reaction? All right, let's get going. And if I look at this molecule, what's different? Ooh, carbonyl. Carbon double bond oxygen. Hydrogen could be R prime, which would be a ketone, but this is an aldehyde. I have my R double prime, hydrogen, and a catalyst. And remember, the catalyst can be nickel, which in this case is platinum, or palladium. And what you get, what's attached to the carbonyl becomes attached to this carbon, which becomes an alcohol. Let me rewrite it a different way. And each atom of the double bond gets a hydrogen. This is my R prime. This is my R double prime, still attached to this carbon. And I'll break the pi bond. Now you could have written this CH2OH like we normally do, but this is fine on a test because I've told you I'm this close to the person who grades the test. It's me. Now on test number 3, that's test number 2, skipped one almost. Test number 2, unlike test number 1, I'll have 3 synthesis problems instead of 1. If I put any more, it'd be cruel, unusual punishment, which I think is still outlawed by the Supreme Court of the United States towards students. So I won't, but let's practice one. And the question would be, what would be the starting material that I reacted with hydrogen and platinum to make that molecule? Remember, synthesis is the fun part of organic chemistry, but I'm biased. I'm a synthetic organic chemist. And thank you all for answering the poll questions. By the way, they're anonymous in case you wondered. All right, let's do it. And the question is, what would be the starting material? What do you react with hydrogen and platinum to make this compound? What's different? Ooh, hydroxyl group on a carbon. This is an alcohol. Now I'll write it this way. And how do we make an alcohol? By reacting with I think the nice weather is affecting my pristine drawing habits here. Remember, platinum is a catalyst. It could be platinum, palladium, or nickel. And you start with an aldehyde or ketone. And here, this is the carbon with the hydroxyl group, which becomes the carbon double bonded to oxygen. Everything else is still connected to that carbon. So I immediately can draw my ring, my methyl group. Here's that carbon, and we'd have a carbonyl. And that's how you do that. Now, before I go any further, quick stop. One of your colleagues sent me a message, and I should warn you, do not put away your shovels and snow blowers. Why? Because back when I was a junior in college, that was April 14th, I believe 1967. Wow, that's a long time ago. But anyways, how do I remember that date? Because the next day was the 15th of April when taxes are due. That's the only time in Northern Illinois they postponed the taxes being due by one day. Why? Because on the 14th, we had about 14, 15 inches of snow. Yes, April 14th. Then the next day it warmed up and we had floods everywhere. Streets were flooded out. Oh, it was an awful mess. And so they postponed the deadline by one day. Luckily, I didn't procrastinate too late, so I already had mine in. But don't put away your snow blowers or shovels yet. You never know. This is Chicago. All right, I'm going to write something on the whiteboard. Do not copy it down unless you want to. You don't have to, though. Now let's look at the following. What if you have this molecule that has both a double bond and an aldehyde in it, and you want to convert this aldehyde to an alcohol? How do you do that? Well, you say, I'll do this. And the answer is no. Why? Because there are two reactions. One you want, which would make the alcohol, but you want to keep the double bond, and the reaction you don't want, which you've already learned, would be hydrogenation of a carbon-carbon double bond. And what you get would be a mixture of three products where this becomes an alcohol, or the double bond is lost and this is not turned into an alcohol, or both are, the double bond is lost and you make your alcohol. And guess what? That's a mess, and you don't want a mess. Well, it turns out this is real life in organic chemistry. And a great organic chemist from Purdue University, Dr. H.C. Brown, Herbert C. Brown, came up with new reagents. This was the end of World War II when these sort of things were needed. And what he invented, one of the two things, which he won the Nobel Prize for in the 1970s, was lithium aluminum hydride, LiAlH4. And think of this like a Grignard, where it's H minus and the rest is a salt. And if you take a ketone or aldehyde and react it with lithium aluminum hydride, first step, second step, acid and water, which I'll write like this. And you get the same thing as hydrogenation. You break the pi bond, Each atom of the pi bond gets a hydrogen. What's attached to it stays attached to it. The beauty of lithium aluminum hydride, it will only attack or react with carbonyls. It won't touch a carbon-carbon single bond. That's because it's more like a Grignard, not hydrogenation with hydrogen. And the question is, what's the organic product? I haven't asked in a while. Thumbs up, people. You see my whiteboard? Thank you. All right. And if we look at this, what's different? Ooh, carbonyl. Carbon, double bond to oxygen. Carbon's here, carbon's here. It could have been aldehydes, a ketone, reacting with lithium aluminum hydride. Second step, acid and water. What's attached to the carbonyl carbon, carbon double bond to oxygen, is still attached. And then each atom of the double bond gets an alcohol or a hydrogen to make an alcohol. In this case, our prime. Here's our double prime. They're still attached to this carbon right here. And I make this isopropyl alcohol. And that's how you do it, which reminds me, I haven't done this today. Did anybody drive by a gas station and think about the gasoline has ethanol? That's an alcohol. Anybody pick up a bottle of rubbing alcohol? It's got isopropyl alcohol and it's got an alcohol.
No, I just noticed it was $3 a gallon.
Well, it's not because of the alcohol, it's from the $3. Aren't you glad you're not commuting as much? You didn't have to drive all the way to ECC and back home. See how much money Dr. White's saving you? Actually, I wish we were commuting. But anyways, two last things. Did anybody happen to look at their nail polish remover and see if it was acetone, a ketone? Don't forget, when you leave my class or our Zoom meeting class, organic chemistry is all around you. I stole that from SpongeBob. And why don't you try this one on this beautiful afternoon in Chicagoland? Or as I like to say, ECC East, where I live, in Schaumburg. And Dr. White used in graduate school, I did this type of reaction where I couldn't use hydrogen, and I used lithium aluminum hydride, second step acid and water. All right, looks like everybody's done. Let's do this. What do we have that's different? Ooh, carbonyl, carbon double bond to oxygen. It's got a hydrogen on there, could have been R prime. And it's got carbons here, R double prime. It's an aldehyde up here, could have been a ketone. We'll call this R double prime, R prime. What happens when you react the ketone or aldehyde with lithium aluminum hydride? Second step, acid and water. You break the pi bond. What's attached to the carbonyl carbon is still attached to it. And this opens up to an alcohol. And if we look here, R prime hydrogen, R double prime, 3 carbons, isopropyl group. Break the pi bond. Now you could have written this as CH2OH, and here I have everything else, but either way is correct on a test. And the question would be the same thing. What would be the organic product or products for the following? Remember, these are the steps organic chemists use to make the products you use in your daily life. Sorry about the delay. I had to get some Kleenex and blow my nose. And now it's all clean. All right. All right, let's do this. I assume everybody's done. What's different? Ooh, carbonyl, carbon double bond to oxygen. This is a ketone. Could have been an aldehyde. Reacted with lithium aluminum hydride. Second step, acid and water. And what do you get? You break the pi bond. Each atom of the double bond gets a hydrogen. What was attached to it? The carbon here, that was the carbonyl carbon, is still attached. Well, here it is, and it's in a ring. So my R prime and R double prime are my ring. Don't forget the methyl groups. You don't break carbon-carbon single bonds. This is my carbon here, and it's an alcohol. Now, if you wanted to put a hydrogen there, you could, but you don't have to. Ooh, let's do one more. And the question would be, what would I start with to react with lithium aluminum hydride, acid and water, second step, to make the following molecule? Your turn. Have a lot of fun. All right, looks like everybody's done, so I better get to work. Now, if I look at the product, what's different? Ooh, carbon with a hydroxyl group, and that's an alcohol, which I can write this way. Actually, a better way of writing it would be this. And this carbon is this carbon with the hydroxyl group. One of these hydrogens is from R prime. The other is when you put it on with the reagent. And what do you start with? An aldehyde or ketone. If I come over here, what's my R double prime? I can call it this. And one of these hydrogens I'll call R prime. So that means I have 1, 2, 3 carbons across, my 2 methyls, and this carbon here is this with a hydrogen and carbonyl, carbon double bond to oxygen. I put in my hydrogens and I'm done. And that's how you do synthesis. I better warn you, the next topic we're going to talk about is almost like the holy grail for Dr. White. It's an area I actually did my PhD synthesis in a very specialized area of the following. But if it looks like I'm having way too much fun, I am. Thought I'd warn you about that. Oh, by the way, this slide I should have taken out. We'll get that for test number 3, not now. All right, now the next couple slides, I'm going to turn the switch, click. Will this be on a test? But it's good background information for you to know about. And we'll get to some of it today and then finish up on Wednesday. And I'll keep my promise, always try and finish up a week before the test. Later today or tomorrow, I'll send out an email. I'm postponing test number 2 that's supposed to be this Wednesday to next Wednesday. Now, there's something called the Keto, Enol, Tautomerism. And Tautomerism, when you have two things that can exist, where you just change in the structure where electrons are and where hydrogen is. And this tautomerism, keto, enol. Now, I got a C board. And here, if I have an aldehyde or ketone, this is called the keto form from ketone, even though it could be an aldehyde. And there's an equilibrium, mostly to this side, but still exists, where I move electrons and a hydrogen, and now I formed a double bond and I have an alcohol, and this is called ene from double bond OL from alcohol. And this is called keto enol tautomerism. And this plays an important role in some reaction I'm going to show you in other chemistry, which I can't get to. If I look at the clock, we're just about out of time. So instead of rushing forward and going over time, no, I don't do that. You know that. I'm going to end a whole 35 seconds early today. And just remind you, don't forget, lab is due this Wednesday. Any labs you haven't, I'm giving amnesty till this Sunday to get them in. And finally, if you need help, come to my office hours. I'll have one tonight from 6 to 7:15 on Zoom. Dr. White should have Zoom expert. No, not really. But anyways, with that, either stop by tonight. And I forgot, I mentioned earlier, but I'll mention again. If any of you want to work together with other colleagues, stop by my Zoom meeting tonight, and I'll set up a private breakout room for you guys to work together. And with that, I'll say, gehen gesund, be healthy. Goodbye.